Hello everyone, and welcome back to this series on financial mathematics. Today we're going to be continuing our exploration of different types of annuity structures, in particular arithmetic increasing and arithmetic decreasing annuity structures. So before we get into this new type of structure, let us first review some of the basics that we've already discussed. So let's consider a very basic timeline, 0, 1, 2, all the way down to, say, n minus 1 to m. And let's consider what we referred to as a level or constant annuity immediate. Right? Annuity immediate. So what was this? So if it's a unit level constant annuity immediate, we didn't have a payment at time t is equal to 0. We had a payment of size 1 at 1, 1 at 2, 1 at 3, 1 at 4, all the way down to a payment of size 1 at time t is equal to m. So if we were to find the present value of this annuity immediate, which we often abbreviate by a subscript n and a half box with I, this was just equal to the discounted version of the first payment plus the discounted version of the second payment twice, all the way down to the discounted version of the last payment at time t is equal to m. And that was the general representation. But we were able to use summation tricks in order to write this in a more convenient manner, in particular 1 divided by the effective interest rate times 1 minus the periodic discount factor to the power of n, where n is the number of payments. Right? So we're like, okay, how often do we actually have a unit annuity immediate? Usually they're, $200 every month or something like that. So we're like, okay, well, if the payments are of size, let's call it m, then our present value, or PV, let's write it in blue. So then the present value of that annuity immediate with equal constant payments of size m, that would just be equal to m nu plus m nu squared, all the way down to m nu n, which, as we already know, is just m times the present value of an annuity immediate with n payments, right? And this is the constant structure for that of loans, right? So now what we're going to do is we're going to consider a more generalized structure. So now suppose that each payment increases by a fixed amount on each time period. So on each time period. So if we were to consider this from the basic timeline approach, what would that look like? So let's again draw another basic timeline. So 0, 1, 2, 3, all the way down to n minus 1 and m. So again, let's assume that this is of an annuity immediate structure. So a payment of size 0 times t is equal to 0. 1 at time 1, and now what we're going to do is we're going to increase this by a value of 1, and that's obviously going to go to 2. We're going to increase that by a fixed value again of 1, and that's going to go to 3, and then we're going to continue this structure all the way down to n minus 1. So obviously notice that 1 matches with 1, 2 matches with 2, 3 matches with 3, therefore the payment time t is equal to n minus 1 will also be t, or the value of n minus 1. And if we add 1 to that particular value, then we have a payment of size n at t is equal to m. So what would the present value of this annuity sequence look like? Well, obviously, if we just use basic notation, the present value would just be equal to the discounted value of our first payment, the discounted value of our second payment of size 2, the discounted value of the third payment of size 3 times, and that will obviously continue all the way down to nu m minus 1 times m minus 1, all the way down to the last payment, which obviously is going to be right after m minus 1, which would just be nu n times n. Right, so that would be the present value, and we can write that present value in a more simplified fashion as the sum from k is equal to 1 to m of k nu to the power of k. Right, because we have the value in front times the discount factor nu k in front of it. Right, so obviously our first payment is of size 1, so a payment or at time 1 is equal to 1, and it increases by 1 each time. So is it possible that we can change this to something, for example, m, and maybe instead of increasing by 1, maybe want to increase by $5.50 each time? So is it possible that we can generalize that value to some number, let's say L, to get the generalized present value of that particular arithmetically increasing annuity immediate structure? And obviously with some algebra, you can definitely derive this, which is what we're going to do next. But before we dive into all that fun algebra, I want you to at least try, as an exercise, in case you haven't proven this identity already, that annuity immediate with m minus k payments can be equivalently calculated as the periodic accumulation factor to the power of k times a ni, so a annuity immediate with m payments, minus annuity immediate with k payments subtracted from it, where k obviously is less than or equal to m. So this is a nice little algebraic exercise that I definitely do leave to you, especially for you financial mathematics people. But with this in mind, I'm going to use this identity in a short moment. Let's get into the algebra to see if we can find a nice representation for the present value of an arithmetically increasing annuity immediate structure. All right, now let's get into the mathematically fun part of this exploration. So as usual, every time we want to find the present value of a structure that we're not really comfortable with, always drawing a timeline is usually a safe place to start. So we're going to have 0, 1, 2, let's do 3, all the way down to the penultimate value and then the last value there. So what we want is we want a payment of 0 at 0. We want a payment of m at 1. We want m plus l, so that's 1 increase. And then we want 2 increases. So notice that the coefficient in front of L matches the index of time minus 1. So notice that that is a 2, that is a 3, so it is always 1 less. So if we go down to n minus 1, this is going to be equal to m plus n minus 2L, and this is going to be m plus n minus 1L there. Right, so what exactly is this? So this obviously increases by L each time period. Right, so that's what we're looking at here. So if we want to look at this in a more easier way, so that we don't have to do any super fancy math. So if we look at time t is equal to 1, and then 2, and then 3, and then 4, all the way down to time t is equal to m, what we have here is an m. We have an m and an l here. We have an m, another l, and then another l. Or technically you could look at that as 0, 0, and then 0. And then we have, for example, at time t is equal to 4, m, l, 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 and 0, 0, 0, and 0. And over here we have m with a bunch of l's on top. And how many l's do we have? We obviously have m minus 1 l's. So why exactly am I writing it this way? Well, if we look at it from a timeline perspective, what we have here is an m, m, m down to m annuity immediate. Then we have an L, L, L annuity immediate. Then we have an L down to L annuity immediate. And then we have our L unit annuity or annuity immediate of size L at that particular thing. So pretty much what I have here is just a bunch of deferments or discounted annuity immediates with 1 less payment, 2 less payment, 3 less payment, and so on. Because keep in mind that all of them do not have a payment at 0, but this annuity immediate with unit or fixed sizes of size L is pushed back 1 unit. This one is pushed back 2 units, and so on, right? So this has 1 less payment, this has 2 less payments, and so on, but they're pushed back into the future. So if we write that in the typical present value structure, what would that be? So we have our m times our annuity immediate structure. So this is going to take care of this first row. And then we have our L times am minus 1 under effective interest rate I. But that's in the future 1 period, so we need to discount that backwards 1 so that this is then lined up into here. And then for the next value, so this would be line 3 going bottom to top, that's obviously also going to be L times AM minus 2 payments. But that's in the future 2 spaces from time t is equal to 1, so that needs to be discounted twice. And then we need to go all the way down to this last L that's stacked on the top, which is only going to be 1 payment of that size under effective interest rate I. And since that is n minus 1 times, that's going to be to the nu to the power of n minus 1, because n will go back to t is equal to 0, but we want that to be an annuity immediate, so that first payment should be at t is equal to 1. So that's the very first very important sequence that you should be able to write. So now let's do some simplification for this structure, and also let's introduce our new notation. So this is going to be an arithmetically increasing, so that's what this A is going to stand for. So an arithmetically increasing annuity immediate with n payments of size I, where the first payment is of size m and increases by L each time. So that is what this statement is. Right? So arithmetically increasing annuity immediate, so that's the I. Annuity immediate, n payments, effective interest rate I, first payment m, increases by L each time. Right? So arithmetically increase annuity immediate with n payments under I, starting with m and increasing by L. So what is that? So that's going to be equal to, so our first payment is M-A-N-I. So notice that everything has an L in it, so I can factor that out. So L times a bunch of these objects. So we have nu A-N minus 1, I, and then nu squared, A-M minus 2I, all the way down to nu M minus 1 times A. And how would you want to write this? Probably n minus m minus 1. I probably would be a nice way to write it, but you should be able to verify that that is just 1, right? But the reason I'm writing it that way is because notice that the exponents on nu, or discount factor, matches that thing that I am subtracting off of n under the subscript, right? So notice that that's n minus 1, and that's m minus 1 too. So this sets it up perfectly for a finite series representation. Right, so what do we have? So we have I-A-N-I under first payment m increasing by L will be equal to m times A-N-I plus L. Now we can go into summation notation, so we're going from 1 to n minus 1, and then we're going to have nu k times A-N minus k, and then I. Right, so that's the first nice representation that we have. All right, so far so good. Now let's go back to that identity I mentioned a long time ago, a few minutes ago. In particular, A-N minus K-I is equivalent to alpha K, and then A-N-I minus A-K-I. This identity. So what I want to do is I want to substitute this identity directly into this expression, and notice that that's going to give us an alpha k and a nu k next to each other. Remember, alpha k and nu k are just reciprocals of each other, so alpha k times nu k is just going to be equal to 1, and that's going to be true for any k. So once I have that, then I can rewrite my present value sequence as follows. So I have a-n, a-i, a-n-i, ml will be equal to m times a-n-i plus l times the sum from k is equal to 1 to m of that difference. So that's going to be equal to a-n-i minus a-k-i. So this is the next representation that we can work with, and yes, that superscript is m minus 1. Now what I want to do is I want to put that into bracket just to be safe, and now I want to distribute this sum over those first two terms and then do some algebra with that. Alright, so now let's get ready for some very fun, not really difficult, but very detailed algebra. So the very first thing that I have here is a-n-i. Notice that nowhere in that expression does it have k in it, which is what that summation is associated to. So what I can actually do is factor that expression out, and then you're just going to have a sum of 1. So it's just 1 plus 1 plus 1 plus 1 plus 1, n minus 1 times, since that's the upper limit. So if we do 1 plus 1 plus 1 plus 1 5 times, that's just going to be equal to 5. So if we do 1 plus 1 plus 1 plus 1 plus 1, n minus 1 times, that's just going to be n minus 1. So that's going to be what this expression turns into. So we're going to have m ani plus l times ani times n minus 1. And then over here, we actually have a nice representation for the present value of an annuity immediate with k payments under I. That's just going to be equal to 1 over I, which again doesn't have k in it, times k is equal to 1 to m minus 1 of 1 minus nu to the power of the upper limit, whatever that is, and that's obviously going to be equal to k since we haven't taken any summations of it. So that gives us this expression. So the next thing I want to do is distribute the summation into the 1 and distribute that summation into the new k. Again, the very first statement, notice, is that 1. So we're going to do 1 plus 1 plus 1 plus 1 n minus 1 times, and that's again going to give you an n minus 1. Notice that there is a minus sign here, so once I distribute this minus sign inwards, it's going to keep that 1 negative, and that minus new k is going to turn that into a positive expression. So let's just figure what that is in just a moment. So that's going to be equal to m ani plus l times, let's do ani, let's not touch this expression quite yet. Let's do minus 1 over I times m minus 1, and let's do plus 1 over I times the sum from k is equal to 1 to m minus 1 of nu to the power of k. All right, so things aren't looking too bad. So if I factor out a 1 out of I, 1 over I, notice that that's everywhere, including in front of here if I put a I over I there. So when I factor out 1 over I, that's going to give me what? So that's going to give me m n ani Annie plus L over I times, then we're going to have I times A and I, and then m minus 1 minus m minus 1 plus the sum from k is equal to 1 to m minus 1 of nu to the power of k, right? So be careful of the little details here. Now let us look at this little piece right here, which keep in mind is I times 1 over I times 1 minus nu to the power of m. Obviously those i's will cancel each other out, leaving us with 1 minus nu to the power of m. What I want to do now is distribute that m minus 1 into the 1 and into the nu n, and then distribute the nu n into the m minus 1. Keep in mind of that little minus sign. So you might want to pause this video and try that on your own so the next step doesn't confuse you. So what is that going to be? So the first thing is going to be that m minus 1 times 1, which is just m minus 1. And then we're going to have minus n nu to the power of m. And then we're going to have plus nu to the power of m. And that's going to take care of the first few terms, right? So keep in mind it's n minus 1 times the 1. And then nu to the n times n, and then the minus 1. Next I want to look at this minus n minus 1, which is just going to turn into minus n. So it's going to be minus n plus 1, and let's just keep that summation there. So sum from k is equal to 1 to n minus 1 of nu to the power of k. Now we have quite a few things that cancel here, which is actually pretty nice. We have a positive n minus 1 and a minus n plus 1. Those things are going to cancel each other out. And if you look here, notice this is the sum from k is equal to 1 to m minus 1, and this is the nth term of nu to the power of n. So we can actually merge that into that and change that upper bound. So once we write that, what are we going to have? So that's ani plus L over I, and what do we have? So we have this minus n nu n, so let's just write that here, minus n nu n. And then we have the sum from k is equal to 1 to n of nu to the power of k. Now this object you should recognize very, very quickly. That is just the present value of an annuity immediate. That is just ANI. So that has a positive coefficient, that has -1, so I can reverse it just for niceness. So then I have the following very simplified representation. So IANI with ML sequence will be equal to MANI plus L over I times ANI minus N nu N. And that is the present value of an annuity immediate with first payment M that increases by L each time period. Right? So very, very nice, simple formula. And obviously you can start to mess with this structure a little bit. For example, if you want to turn this into a perpetuity arithmetically increasing structure, then obviously you just take n and send it to infinity and you're going to get some structure, right? So that's going to be m a infinity I. That's going to be your typical and perpetuity immediate. And over here we have L over I. And then over here we have, again, our perpetuity immediate. Nu to the n is going to go to 0 and vanish that term out. So that's just going to be minus 0. And then we can just use the formula that the present value of a perpetuity immediate is just 1 over I. So this is actually just going to be equal to m over I plus L over I squared. Right? So it's IA infinity I m L. Right? So that is our present value of an arithmetically increasing annuity immediate. Right? Are there several other formulas that you could derive? Of course. I'll list a couple of them out that you definitely should try on your own, especially if you're in the mathematical finance world. So the present value of an annuity due that is arithmetically increasing under the same exact change should be equal to something. Another one is IA double dot, or the present value of annuity due that is a perpetuity. Just send n to infinity and you can get that identity. And you can also consider the future value at some particular time under ML, so that's for an annuity due. And you could also develop an identity for the future value of an arithmetically increased annuity due under the same exact structure. And those all will have their associated formulas that are very good mathematical algebraic identities for those of you in the theoretical realm. Right? But these main two that we've derived as annuity immediate and perpetuity immediate can easily be transformed into these other four using the same exact identities we derived before. So now that we have our primary algebraic formulae, now I want to use a real-life example to sort of compare this from the perspective of loans to see if arithmetically increasing monthly payments for loans actually is in our advantage on the consumer perspective. So let's assume that we take out a loan of $82,000 under an annual percentage rate of 4.1% for 6 years, aka 72 months. You should be able to verify that if you make equally sized payments at the end of every month, your monthly payment will be $1,283.84. And that obviously, since the payments are fixed and not changing with no deferments or no balloon payments or drop payments, L will be equal to 0. That is, it technically is increasing arithmetically by a value of 0 each payment. So the natural question that we want to answer today is, does structuring this loan under an arithmetically increasing annuity immediate with L greater than 0 help out the consumer, the business, or both? So another thing that you should be able to calculate under L is equal to 0 is that if L is equal to 0, the amount in total that you'll pay towards interest, keep in mind, is the total amount paid, n times the monthly payment minus your principal, will be equal to $10,436.20, right? And that's obviously going to be over 6 years. So if the bank can get more than that, then obviously the bank will be happy. If it gets less than that, the bank will not be happy. Keep in mind, for an arithmetically increasing loan, our original payments will be smaller than usual because our latter payments will be larger. So it's pretty much like a sequence of drop payments and balloon payments that are offsetting one another. So let's assume that, suppose that we want L to be equal to $5. So every single month, your monthly payment will increase by $5. So what will be M, which is our first monthly payment that we will start stacking on top of? So keep in mind the present value, which obviously is going to be our principal, must be equal to IANI of M to 5, right? And our goal is to solve this equation for M. So what is that going to be? So that's going to be equal to M, A and I, generally speaking, plus L divided by I times A N I minus N nu M. So there's only one thing that we need to solve in this equation, and that's obviously just that little M term. So we can just isolate this particular object, solve for M, and you should be able to see that M, which is associated to the monthly payment for the first month, will be approximately equal to $1,113.56, right? And this, again, is the amount at time t is equal to 1. So how much money will you need to pay at time t is equal to 2? So M2 will be equal to M plus L, right? And again, M3 will be equal to M plus 2L. And you can continue that payment, and keep in mind the generalized structure would be MK is equal to M1, or technically M, let's just call it M, M plus K minus 1 times L. So that's how much the monthly payment will be at time t is equal to K. And this is for K is equal to 1, 2, all the way down to N. Right? So we know what our base amounts, which is obviously slightly lower by about $150 than our first payment. It's going to increase by $5 each time, and eventually is going to surpass our original base payment. But how does the interest change? So how much do we end up paying to the bank? So it's obviously going to be the sum from K is equal to 1 to M of our monthly payment at time t is equal to K. So maybe we can just keep this in the general form to get a nice little formula for this. So what is that? So that's going to be equal to the sum from K is equal to 1 to N of M, our fixed base payment, plus K minus 1 times L. There's only one thing that has K in it, so everything else is a constant as far as this summation is concerned. So what I want to do. So keep in mind, again, we're going to be adding 1 up n times here. So again, we can write this as the sum from K is equal to 1 to N of M, and then we can distribute this L inwards, so that's going to be minus L for the first term, and then plus K here. And then we're going to distribute this summation over that sum. And then we're going to be adding up 1 n times. So 1 plus 1 plus 1 plus 1 plus 1 n times. Why is it n? Because that's the upper limit. So that's going to be equal to M minus L times M. And then over here we have the sum from K is equal to 1 to N of K. So what is that summation at the end? Keep in mind, that's 1 plus 2 plus 3 plus 4 plus 5 up to n. So that's our very typical arithmetic series that you probably know the value of. So we can actually write our formula as follows. So it's going to be m minus L times n plus n times m plus 1 all over 2. So using our value of n, you can actually find that this is going to be approximately equal to $82,444.35. So that's how much money we're going to be end up paying back to the bank. Remember, we actually only borrowed 82 grand. So if we only borrowed 82 grand, and this is how much we're end up paying, we actually didn't pay that much in interest. So keep in mind, I total is going to be equal to the amount we paid total to the bank minus our principal, and in this case, that's approximately $444.35 compared to the $10,000 that we paid for a fixed annuity immediate, right? And keep in mind, this is over 6 years, right? So who won in this negotiation? That's obviously us. The bank definitely lost out on a lot more money. They almost lost 10 grand on that contract switch. This is why you're rarely ever going to see loans structured in this way. So even though loans aren't usually structured in this way, loans are easy to understand for this type of example, this is commonly a strategy for investing money into accounts when you usually do not have as much money up front on the front tail of the timeline, and you have more money on the right tail of your timeline, which is often common for small businesses that are just starting up and usually gradually develop their profit margins over time. So this usually benefits them as well, since they don't have to cut into their profit margins as deeply on the front end of their business life. So that's just one common variation that is imposed on annuities, in particular annuity immediates, and this is called arithmetically increasing. There's another type of increasing loans called geometrically increasing annuity structures, which we'll talk about in the next video. So I hope to see you then. Take care.